Now, the only way in assembly that we can perform operations on data is to have them loaded into registers that can then be processed and then stored back out someplace. So the LC-3 has 8 general purpose registers, R0 through R7. These are all here just temporary memory locations just for doing operations such as add and not. And we're going to use these in our program by first putting information into the registers and then executing the appropriate instruction, the arithmetic or the logic instruction that you want to do on that data. So step one in doing an operation like that is to get data into the register. Besides the registers here, we're going to be paying attention to one other register here, the CC register. This is the condition code register. And as things are loaded into registers from memory or from hard-coded values, that condition code register is going to change to indicate whether the value just loaded is negative, 0, or positive. So we're going to watch that as we go through these different processes to get data into and out of registers. We're going to watch the condition code register to see how it changes. Now, the simplest way to get data into a register in your code is to use an immediate value, and that is a hard-coded value. This is a 0. This is a base 10 value of 5, and these values are placed into the registers directly through an arithmetic or logic operation. So we don't have a way to directly put data in other than anding or adding to an existing register. So this first instruction takes whatever's in the R0 register and ands or performs the logical and operation to that value and 0. And if you recall from when we talked about number systems and logic, that anything ANDed with 0 is going to end up 0. And it's going to store the result of ANDing these two values into R0. So R0 is going to be effectively erased of whatever it currently contains and will be overwritten with all zeros, all binary zeros. And that is a way, as the comment says here, to clear the register. This next instruction is going to take whatever is in R0, and we know it's 0 because we placed it there. We're going to add a positive 5 to that value, and we're going to store it again in R0. So first we're going to clear the value out, set it to 0, and then we're going to add a 5 to that 0 to get the value of 5 into R0 to then do some further operation. So this is typically a two-step operation. The first step here with the AND to clear the register out is necessary because you don't know what is in a register to start with, and the only way to get a 5 into this register is to add it to what's already there, and in this case the 5 that you want to add. So you need to make sure that this is a 0 if you want 0. If you're doing something like a loop where you're adding a number, incrementing a counter or something like that, then you don't want to 0 that out. But you do want to initially set it to 0 so that you're guaranteed when this line executes that our 0 will contain a 5 and not some other value because there was already something in our 0. So assembling the code successfully and switching over here, we can see in Simulate that we've got our 2 lines of code here. Technically 3 because halt is a separate line of code, but it's just simply stopping the program from running any further. So we're at this line of code now. Our 0 already contains a 0. There's no guarantee each time. I just reset the simulator, so it gets reset to 0 automatically, but that may not always be the case. So good to zero out a register before you put a hard-coded value in. So when I step over this line, that's executed. Nothing has really changed because it already was a 0, but if there was a value in here, it would have been changed to 0. And then we can see the condition code register is a Z, indicating that the last result of the last instruction was 0. So ANDing anything with 0 is going to result in a 0. So that makes sense. Okay, now we're going to finally put that 5 into R0. And when I step over this, we see that we have the 5 in there now. So the previous 0 added to a hard-coded 5 stored in R0. We have our 5 as expected. We can see the condition code register now registers a P for positive, indicating that the result was a positive value. So at this point, we have a value that we want in R5 ready to do something with. Another way to get data into registers to perform operations is to load them from memory. So as you can see, this program is much more complex than the previous one, and that is because we have allocated these 3 memory locations, given them names or labels to refer to them in the program, and then put hard-coded values into those memory locations. So this first one, my data 1, will contain a base 10 value of 10. The my data 2 contains a hex value of FF, and then my value 3 contains this binary value. So you can see the pound sign indicates that the value is a decimal or base 10, X indicates hexadecimal, and B indicates binary. So you can use whichever you would like, just make sure that if you're using hex or binary that you've got the correct value here that you want loaded into memory. So with this, we have memory filled with information ready to be loaded into registers. Up here in our program, our first line of code is going to load from the memory location that we've given the label MyData1, which we have holding the 10, into R0. This value here in MyData2 is going to be loaded into R1, and this value in MyData3 will be loaded into R2. One thing to notice from the immediate value example is that we are not clearing the registers out first. We don't have to, because we are transferring all 16 bits from the memory location, such as my value 1 or my data 1, directly into the register. So any bits that were there before are getting overwritten completely. So we don't need to zero out when loading from memory. So assemble this. And so we can see before we start, we're here at line or memory location 3000, our first instruction. But let's take a look at the program all the way through to halt. So there are our instructions. And then here are the 3 memory locations that we allocated. We actually allocated 4, but I will talk about this 4th one in a little bit. So we have this memory location, which we gave a label of MyData1, which contains 10. MyData2 contains a hex FF, which is in base 10 is 255, and this binary value in MyData3 is this negative value when converted to base 10. So as we go through and execute each one of these registers 0, 1, and 2 are going to be filled with 10 FF and then this binary value. We will also see the condition code register change with each one of these loads. So besides and add modifying the condition code register, loading data from memory also sets the condition code register. And we'll talk about why that's important in a separate lesson. So walking through this, execute our first line here, and now we have that 10 in R0 as we planned. And now we've got the 255 in R2. You can see our condition code registers was positive here. It's now positive again. And since we have a negative value here in MyData3, when this gets loaded, we should expect this to change to N for negative. Step over that, we have the value in R3, and sure enough, the condition code register is negative. So at this point, we have 3 registers loaded up pretty quick, although we can't see it, but it took more clock cycles to complete. We have the values loaded up and ready to do whatever it is we need to do with them. And once completing an operation on data, you may want to store the result of that operation back out into a memory location. And so this code does that. A little bit different here. We've got my data 1 and my data 2 from the previous example, and then we have result. We don't need my data 3 for this example, so I removed it. So we have these 3 allocations similar to the previous example. The code is different. We load the first 2 memory locations that we set up here into R0 and R1. Then we perform an operation. This is going to take the value in R0, which will be my data 1, which will be 10. The value in R1, which is my data 2. It's going to add those 2 values together and store that in R3. Okay, so we're going to actually perform an operation on the 2 values that we loaded from memory, and then here's the store instruction, and that says to store whatever's in R3 into the memory location or memory label of result. So we will see memory get updated with the result of adding these 2 values. So switch over here, and just like before, we will step over these 2 instructions. These 2 registers will be loaded. The condition code register will change each time. So there we have the 10, there we have the 255, and now we're here at the add. So we should have 265 stored here in R3. All right, so there's the result, and now we're here at the store instruction, and now what we should see is storing this R3 value, 265, into this memory location. So we will see this value change from just the default 0 to 256 when we step over this line. And there we go. So now we've written the result back out to memory. So we've taken 2 values in memory and added them together and stored the result in another memory location. And the last thing to talk about here is naming the memory location. So the labels that were put in the code to reference each of these memory locations were my own names, kind of like variable names. In assembly, we call them labels because we don't really have variable names. Variable names have a different meaning in higher level languages. But this is a label that the assembler uses to connect this memory location, which at this time we don't know what memory location this 10 is going to be placed into, but the assembler can figure it out and then reference this memory location by this name so that when we use it in our code, it knows that to go to that particular memory location. It's important that these are unique and are not any of our LC-3 instructions or pseudo-ops or other keywords in the language, just like when you name variables in Java. You can name them whatever you want, make them descriptive so it's obvious what they are for you and for anyone reviewing or maybe grading your code, but just make sure that they don't clash with anything that the LC-3 is already using. And you may have noticed a difference here. We have labels here of my choosing. These 2 use another pseudo-op, a .fill and a .block word. The .fill allocates one chunk of memory and puts a value in it, fills it with this particular value. We're doing the same thing here. The .block word is a different pseudo-op that allocates memory but does not put anything into it. In this case, the 1 represents one memory location or one chunk of memory. So result is a label that references this memory location, and we've only allocated and cleared out one of those locations. So when we look here, before we ran our program, this memory location was set to 0 because we didn't use a .fill and put anything in it. We just allocated or reserved this memory address for something that we were going to do later, which is where we stored the result.